In the last video, we were talking about stationary phases and why things move up the stationary phase like they do or through the stationary phase like they do. And we went a little bit deeper into some organic chemistry, not much, but a little bit. I think it would make some kind of organic chemistry teachers very happy. Or it might have cleared up some things that you took in organic chemistry and you're like, I don't know what I'm doing. I just passed it just because I got lucky. And then you maybe heard that lecture and you're like, well, why didn't I understand this back when I took organic chemistry? Well, if you are one of those camps, then congratulations. I applaud you. Yay! Woohoo! So now we're going to truck on. And what we're going to truck on with are some abbreviations that we will see in the box that our silica plates come in. So the very first one is going to have a F. And an F just basically means it is a fluorescence indicator. That is what this is. So that means that this has been mixed. The stationary phase that I've chosen, whatever stationary phase that is, it does not matter. But I have mixed in a fluorescence indicator to the label. And just so you can read my chicken scratch, I'm going to pull this up on my screen. So the fluorescence indicator is the idea that I can mix something with it and my compounds can maybe glow. Yay! So if you did the drug slide already in our lab experiment, then you've already seen this. You took that silica, you put it on a light box, and when you put it on a light box, it glue. Oh, look how pretty, it's neon green. Well, the reason that it's neon green is because it had a fluorescence indicator that was mixed into the silica or the stationary phase, and that UV light box responds to that fluorescent indicator quite well. We'll talk about what this indicator is a little bit later on, but that is what the F stands for. So there was a issue one year, and that issue was, and I will not tell you names, absolutely not. I'll just say that there was some maybe chemistry classes that were going on, and they were developing plates, and all of a sudden their plates were not coming out, and they were like, we don't know what's going on, Tracy. Do you know what's happening here? And then I would look at them and I would say, well, let me see the plates that you're using. Let me see the plates that that you've ordered. So, oh, it's always worked. It's always worked. We've never had a problem, and I don't know what's going on. I think our stuff is bad. And I'm like, no, your stuff is not bad. We still use things back in the 1970s and it still works perfectly fine. At least for academics, absolutely it does. So no, your stuff's not going bad. So what I did is that I looked on the box of the plates that they ordered, and their box did not have fluorescent indicator because they didn't quite know. They just thought that all the silica came with a fluorescence indicator, and it's a no. That's not how this is working. That is not how what goes on in real life. If you want the silica to glow under a light box, because that's how your components will respond, you need to make sure you put a fluorescence indicator in there. And they ordered a big old box, and that box was silica plates, and that had no fluorescence indicator, so it wasn't going to do them any good. That's why they didn't see spots. That's why nothing showed up under a UV light box, because they just made an assumption. So that's what the F stands for. The 254 is the nanometer, which is the wavelength that the fluorescence indicator will appear. So there's different options with fluorescence indicators. 254 is the most common. That is what you will see very often. And for that reason, you will often see F254 that will happen on the surface of a label. Well, it doesn't have to be 254 though. There are other wavelengths that are out there that we can utilize that will glow under certain circumstances, and you get a few choices that are out there. But that 254 is basically telling you the nanometer that is the most appropriate for those components that you want to kind of see, that you want to analyze, that you want to do development with at the end of the process of TLC or HPTLC. Next up are the RP2s, RP8s, RP18s. These are pretty common on the boxes as well. You want to make sure that you don't grab a box that has some of these. So we do actually have these silica plates in house. And whenever you go to the box of silica plates and you grab one because you want to analyze it for that day, you want to make sure that you're grabbing the appropriate ones. And for the most part, we need the silica versions. And you want to make sure it does say silica on the box. So it will specifically state silica. I mean, it will write that word on there. If it is not silica, you will see RP, and then there'll be a number. 2, 8, or 18 are the most common. And now you know what those numbers mean. Those are, flip it and reverse it, Missy. Those are the reverse phase types of stationary phase that we can use because we want a non-polar plate. We don't want a polar plate for the analysis. So there's 2 carbon chains hanging off of the silica. There's 8 carbon chains that are hanging off of the silica. There's 18 carbon chains hanging off of the silica. That's what those are. All those carbons are holding hands one after another to make these really long trains of carbons that are the really long fingers that's coming off of the stationary phase. Next up, another common digit I'd like for you to know is the 60. And the 60 that's highlighted on your screen is actually the diameter of the silica particle. So we can get really huge silica particles, and you kind of seen that before. You ever bought like something in the linen department, or a pocketbook, or a book bag, or something, and you see those kind of big silica gel packets that are on the inside? That's what we're talking about. Well, if you opened up those packets, there's a chance that some of those are going to be fairly large beads. And that is a very large diameter. Well, we can take those beads and we can grind them up and we can turn them into a really fine powder. Well, if we do that, we want to make sure that it's universal, that all of them are kind of the same size, and we can grind them up to a certain point where they go 60, and that 60 represents the diameter of those silica particles in angstroms. So 10 angstroms is around 1 nanometer. That gives you an idea. So super, super tiny. In other words, what I'm saying is that this is very light, fluffy powder. So silica 60 is the most common type of plate that we will see, that we will use. But depending on what you're doing, you might need maybe a finer ground up particle size, or maybe you don't need it that grounded up as much. But 60 is going to be pretty common, and that is going to be the basics of plate theory and how these things begin to separate. So silica is normal. The normal phase is how we run them most of the time. And then silica is going to be the most appropriate size of the particle that we will see in a laboratory setting. Some of the others, not necessarily as important. I will say, though, that the MS stands for, if you've taken the spectroscopy class, just what it did in that course. It is a mass spec version of a plate. We can connect mass spectrometers to TLC instrumentation, and that will do like little punch outs of plates, and it will take that compound that has traveled up the plate to that distance, and then it will clean that up and it will send it through a mass spectrometer. And when it does that, we can get some mass spectra data on that particular component. So we can still do mass spec on HPTLC, believe it or not, but we need some instrumentation, we need some modification to that equipment, and currently we do not have that in-house. We probably never need that in-house, but who knows? Maybe one day we'll look up and we'll get one. I don't know, but that is an option of things that we can do. Down at the very bottom, you see G. G is going to be our gypsum, and gypsum is the bonder. So when they grind up the silica particle, it's a very light, fluffy powder. They need to place it on a glass plate. And I'm sorry to tell you, it just doesn't stick, okay? So normally what happens is that we've got to make a slurry, and that slurry will very often have a solvent in it. So we take the solvent or liquid that's going to eventually evaporate, and then we mix it up with our silica, and then we mix it up with some binder as well. So that way, when that liquid evaporates off, what we're left behind with is the silica that's got a little bit of binder in it, and that binder helps it adhere to the surface of the glass or the plastic or the aluminum, whatever we decided to use. That is kind of the purpose of the binder. So almost everything will have binders, absolutely, almost everything will, but that is how they're made, and very often you'll see G on there just to let you know that gypsum was used for that bonding agent. So you're going to see that these abbreviations are going to show up in Canvas questions. Be ready for them. I like the highlighted ones. Those are the ones I gravitate to. They are the most common, and they're most applicable to us making decisions on what kind of plate that we need in order to operate. All right. Next up, now that we kind of know this idea of what's on a label of a plate, I want to change our focus now to our mobile phase. And our mobile phase is going to be just as important as the stationary phase. So this is very often they call a solvent, but it can also be a mixture. So when they use the word solvent, they are sometimes talking about a pure substance which means it's just one thing only, and that is it, nothing more. So, for instance, toluene. Toluene might be a solvent. Toluene could be an appropriate mobile phase for the analysis that I want to do. And if so, that is perfectly a-okay. That is not an issue at all. But they normally kind of gravitate those and call them solvents. There's another word that we will use here, and that other word can also be called a neat solvent. And the word neat just means that it is just one thing and one thing only. It was poured straight out of the jug and into the chamber or the tank that my plate is going to go into. Next up is a mixture. Mixtures are also pretty common, but these mixtures, I'm going to say, have around 2 components, but nothing really more. And I'm going to put approximately 2. There are chances that I will see 3, but very often we try to keep this simple, and we want 2 solvents if we're going to mix it. We don't even like to have 3. If we need 3, we can do them, whatever. But 3 is kind of pushing it. We don't really desperately want anything more than 3 at all. It just overly complicates the developing and how that is taking place. So that is a mobile phase term that we can use, neat solvents versus mixtures. And we can talk about what we call solvent strength. All right. So solvent strength is the idea that things begin to separate for us. And as things begin to separate onto the plate, well, we can control that separation by making the solvent stronger or weaker, I guess is how you can refer to that. Now, there's another term here that we're getting ready to talk about. And the reason I'm pausing and slowing down is just to maybe probably get your attention at some point in time. But there is a thing called a developing solvent. And a developing solvent is not the same as mobile phase. They are different. And we're going to talk about why here in just a second, but they are different. All right, so what this means is that if I pull out a neat solvent, that neat solvent, so for instance, that toluene straight out of the jug, that is a developing solvent. If I make a mixture, and this mixture is a 2-component mix, then that is a developing solvent. Okay? The solvent strengths I can play with. So this is separation power. So normally what happens here is that you play around with the percentages. So 60-40%, absolutely. 50-50%, absolutely. So if I do something like methanol and water, okay, there is a mix that I am making. It's going to require methanol, it's going to require water to be mixed together in a certain ratio. Okay, not a big deal. What is the ratio? Okay, well, that ratio is going to be a percentage. That percentage is going to change the strength of that solvent system. And it's going to be able to do different things for me. And those different things can actually be done with very small changes in percentages. 60-40, 50-50, 55-45, if that's a thing, right? I mean, it doesn't take a lot to see drastic changes sometimes. Well, all of these are called my developing solvent. These are not called my mobile phases. They are not the same. So you know as good as well as I do, that is going to be a Canvas question. You're going to see us go in and write questions, and it will talk about the developing solvent is the same term as the mobile phase, true or false? And you're going to put false. It is not the same term. They are different. The developing solvent is what I'm making in a laboratory environment that I will be using in a TLC or HPTLC analysis. That is what I'm mixing. That is what I'm making. That is what I'm in the bottle. That is what's going to go in the tank. That is a developing solvent. Mobile phase is different. And the reason is because the mobile phase is the stuff, and I'm going to put this in quotes, that travels through the stationary phase. That's the mobile phase. And now you're scratching your head. And now you're saying, well, wait a minute now. Wait a minute. How does this even make sense? if I'm making a developing solvent and I'm pouring that developing solvent into the bottom of this tank, you're telling me that that's not the mobile phase that's going up the plate? No, it's not. And we've kind of already mentioned this. Because what's going to happen here is that I'm going to make a developing solvent. I'm going to take something and I'm going to pour it into that tank. And when I pour it into the tank, I'm putting a lid on it. And the first thing that I'm going to allow happen is bloop, 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 bloop. It's going to create gas phase. And this gas phase has got to come from somewhere. And that gas phase are volatile components that's coming from your developing solvent. That's what this is. So for instance, let's say that I make a 50-50 mix of methanol and water. I pour it into the tank. That is my developing solvent. I put the lid on it and I wait for 20 minutes. That's pretty standard. As I'm waiting for 20 minutes, what's happening here is that there is a chance that my methanol, because it is very volatile based on how it's built, is leaving that water. There's a chance that it's going into the upper realms of the TLC chamber. And if it is, and if it's evaporating, and it's leaving, then guess what, folks? The developing solvent that I made, that I poured in here, this is not the same stuff that's going to travel up the plate once the plate goes in. And the reason is because I started with the 50-50 split of methanol and water, but methanol is evaporating off. Methanol is losing out of my developing solvent. And that means that the concentration of water is going to be kind of larger by the time my plate gets in there. And the concentration of my methanol is going to go down because it's evaporating and it's escaping. So by the time my plate goes in, there is a chance that it's no longer 50-50, but there's a chance that it might be 70-30 now. That's the mobile phase. That is what that plate is going to see once it gets dunked inside of the tank, inside of that mobile phase. And once that mobile phase starts getting into the stationary phase and soaking up through the plate, that composition could be changed. Now, there is a chance that it might not be. There's a chance that nothing is volatile. There's a chance that you use the neat liquids, so it doesn't really matter. Neat liquids are neat liquids. There's no composition changes that are beginning to take place. But if it is a mixed solvent, and if you do have components that are volatile, by the time your plate gets dunked, that developing mix that you did, that you made, it's no longer what's in the bottom of that tank. And that's because the gas phase has been created, and that gas phase has made an impact into how this plate is getting ready to separate. Because you thought you were making 50-50, but by the time the sample sees it, it could be totally different. You don't know that. It could be totally different by the time they get dunked. So those are the things that you got to keep in mind. As far as solvent strengths go, we've got kind of an image here that I like to talk about just for a few minutes. This image is basically showing you a 100% hexanes to the left-hand side. And we are beginning to change the percentage of hexanes as we go little bit by little bit by little bit by little bit. So from slide to slide to slide to slide to slide. And what we're mixing it with is ethyl acetate up here at the very top. So in the 100% hexanes, we've got 0% ethyl acetate. And if you take a look at that very first lane, well, you're seeing there's no separation at all. That stuff didn't even move. It didn't even move from the origin. Nothing took place. So we know, okay, this is not a very good developing solvent. It's not a very good mobile phase. Separation is not taking place. It didn't even move from the start line. So when we go back to the drawing board, we're like, okay, well, what can we do to change it? We can change the stationary phase. We can change the mobile phase. We can change every blah, 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 blah. If you do change mobile phases, that is fine. But you need to change mobile phases in little bitty baby steps. And the reason is because look at what happens. If we just change it by 5% and we go to 95% now instead of 100, and we include 5% ethyl acetate as a second component, we see 4 bands. Now I see the purple one that's staying quite down at the very bottom, but look at what I did in 5% changes. That's all that it took, little bitty baby steps. It showed me an orange band and a pink band and a yellow band. So there's multiple components that are there, and it did separate some of these. Right now, did it separate all of them fully to the best of its capability? No. But look at what 5% changes did. So when we do go and change our mobile phases and our developing solvents that we are using for TLC and HPTLC development, we are going to be baby stepping, baby steps, cuckoo. That's what we're going to be doing in these changes that we are going to be taking place. Okay, well, let's say that I completely flip it and I go all the way down to 10% hexanes and 90% ethyl acetate. Look at what has happened. The purple left, absolutely the purple left, and that purple left because it probably saw that new mobile phase, and that new mobile phase with ethyl acetate, and that ethyl acetate was a little bit more polar than what the hexane was, so of course it enjoyed the ride, and it just pew, went straight up. All right, so what's happening here is that everything left and everything kind of approached to the top. That is also not a good situation. We do not want something like that to happen. So what is kind of the thing that we're after? Well, if you take a look at the one before, look at the yellow and the orange here. What happened to the pink, right? There was a pink one that showed up here, a pink one that showed up there, a pink one that showed up there. It is now getting disappeared into those bands again. So there's going to be a little Goldilocks area that we would prefer our samples, or at least our compounds of interest that we want to monitor, and the compound of interest that we want to report on. We want to make sure that those go a certain distance up the plate, and if they do, then that is great news, and then we've got a pretty good solvent. Now, if I'm not interested in reporting everything, if I just want just one little bitty piece of all the spots that begin to show up, then you're going to see us kind of focus in on that RF. We're going to focus in on making that RF the best that it can be. But there's going to be a time here that we need to talk about appropriate distances and what we like to see as far as the retention factor of how these components are traveling up the plate. So this is the solvent strength, and this does affect resolution, and very, very tiny amounts of changes can happen that will affect our separation quite drastically if we're not very careful. So in the next video, we're going to pick up from here. There's more that we want to talk about solvents. And this time we're going to talk a little bit about going to church, and we're going to talk about our Holy Trinity. So we need to come back, talk about the Holy Trinity, the Father, Son, the Holy Ghost. And then we will talk a little bit more about solvents and how we pick them and how we can determine maybe which one is the best for me to use if I was in a little bit of research and development.